Hi, welcome to educator.com. So, this is the beginning of physics. We're going to do first, though, before we get into the physics, we're going to do a quick math review. So even if you feel really strong with math, just make sure to real quickly skim through this section because you want to make sure you understand all these concepts because they might come up in this course and they might also come up in whatever course you're taking if this is a supplement to your other physics courses. So, it's a good idea to make sure you've definitely got the background and the skills inside of this math review. So, let's get started. First off, the metric system, also called SI units, which is from the French Système International, which is the people who first created the metric system and first propagated its use. So, the metric system was created in the 1800s to, actually maybe the 1700s. I should know that. Anyway, I'm sorry. Anyway, the metric system was created to standardize measurements, and it's done a great job of that. Almost all the countries in the world, with the exception of the United States of America, are completely standardized on it. And even in the United States, everybody in science and physics, they all use the metric system. The metric system is great, and it's the way to do things. So the basic units we work with in physics are distance, which is the meter, denoted by a small m, mass, which is the kilogram, denoted by kg. And I like to point out it's the kilogram, so it's not actually the gram that we consider our basic unit of mass. We consider the kilogram our basic unit of mass. Just an interesting thing to point out. The volume, which comes in liters, denoted by a small l, or sometimes a cursive L if it will get confused as a 1 sometimes. And finally, time, the second, which is denoted by s. All right. Scientific notation. What if we had a problem involving the number, say, 47 billion, or 0.0000002? If you had to write that number more than 2 or 3 times, I think you would be unhappy, and I think you should be unhappy. That's a lot of times to have to write a number. That many digits, it's just a pain. And you're not really putting in much information, it feels like, in those zeros. So we wouldn't want to have to write that all those times. So how else could we write it? The trick there is scientific notation. The idea here is you can convert it by using powers of 10. So 47 billion is the same thing as 47 times 10 to the 9th because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, so times 10 to the 9th. And if we wanted to have it so we only had one digit at the very front, we could push it over even one more and we could have 4.7 times 10 to the 10th. Same idea if we want to move a digit up. We go back 1, 2, 3, 4, 5, 6, 7, 8 spaces. So that would be 2 times 10 to the negative 8th. And we're able to compact information this way because 10 to the 1 is equal to 10. So 10 squared is equal to 100, and so on and so forth. And we can also go smaller by using 10 to the negative 1 is 0.1, so 10 to the negative 2 is 0.01. This allows us to slide digit around so we don't have to write really, really long numbers. Because when we're dealing with, say, the number of atoms, or the charge of an electron, or the distance from here to the sun, we're going to be dealing with very large and very small numbers depending. So physics deals with some very extreme values, and we don't want to get cramps because we have to write 30 zeros every time a number comes up. Significant figures, also called sig figs. Significant figures are a way of showing how precise our information is. Since all measurements are susceptible to some amount of error, even if you look at a really fine ruler, it's hard to tell if it's the difference between 1/100th of a millimeter to the left or the right. There's always some amount where it's a judgment call and you might be slightly wrong, where there's always uncertainty in every measurement. There's always some little bit of possible error. So a significant figure expresses how certain we are of our measurement, or what the uncertainty in the measurement is. It says how much we can trust our info. So significant digits give us a way of letting us know how much we should rely on the information we have. Which digits are significant? That requires a little thought. So a significant digit is any of the following. Any digit that is not a 0, the zeros between non-zero digits, and zeros to the right of significant digits. So the only digits that aren't significant are digits to the left of non-zero digits, which makes a lot of sense. If I wrote 2 and then I wrote a bunch of zeros in front of it, well, that's the exact same thing, right? And there's no way to measure the difference between 2 and 2 with zeros in front of it. So it means the exact same thing. There's no way you can measure a difference, so there's no significance in all of these zeros. We wouldn't care about them, knock them out, so this would only have a significant digit of 1. One significant digit, one sig fig. But let's try some other examples. So our first one, we've got 1, 2, 3, 4, so this would have 4 significant figures. This one has 1, 2, 3, and what about that times 10 to the 4th? Well, it times 10 to the fourth. If we were to have 10 to the fourth, well, that would be 10300. So 10,300. But if we had 10,300, what we'd be saying is we had precisely measured 10,300, precisely measured 10,300 meters. But what we really did was we only managed to precisely measure the first 10,300, but it might be up or down a little bit there. It could be 10,349 or 10,251. It could be something that's close to that. We would round to it, right? We're only sure up to that 10,300. So that's the point of the sig fig here. So that scientific notation also gives us the ability to show the information that we have measured for sure, but there might be some past just the zero. So it's not multiply out the scientific notation and then find the sig figures. You find the sig figs before you multiply the scientific notation. So this one would have 3 significant digits. Here we have 1, 2, and then all of these are zeros, so it just has 2 significant digits. Here we have 1, 2, 3, 4, 5, so it has 5 significant digits because these ones don't count, but these ones do count because they're to the right. It means that you measured something precisely. There's a difference between if I say, yeah, I weigh about 75 kilos, right? I weigh about 75 kilograms. Or if I say, I weigh 75.000 kilograms. That means I've managed to get a really, really precise reading. I am down to within a gram certainty of my weight. So that's a very precise reading of my weight, a very precise reading of my mass. So that 000 at the end matters, but at the front, once again, there's no extra information there. Finally, if we had 4.700, well, we'd have 1, 2, 3, 4. We count from the right in, or the left in this case, because there's no zeros to the left. So zeros on the right, they count. Here we'd have 4. Awesome. How do significant figures interact with one another? So if you add, subtract, multiply, or divide numbers, we have to pay attention to how the significant figures interact. The resulting number is only going to be able to have as many significant figures as the lesser of the 2 numbers of significant figures. The smallest number of sig figs is the number you start with becomes the number of sig figs your result has. And this makes sense. If I know I weigh precisely, I have a mass of precisely 75.000 kilograms, but then I get on a boat with somebody else who weighs about 80 kilograms, I can't say together we weigh precisely 80 plus 75, precisely 155.000. I can't do that because I don't know, maybe they weigh 83 kilograms. They were unsure when they told me their mass. So I can't be certain of it. It means that we have to go to the least significant digits we had, which was either those 2, which was those 2 digits of 80 significant figures, of 80 kilograms, so we've only got 2 significant figures. Okay, so if that's the case, we'd wind up actually having to round up because we'd have 155, it would become 160. Okay. So here's some great examples. If we have 2 kilograms here and 0.0803 kilograms here, mathematically we add them together and we get the number 2.0803 kilograms. But this guy has 1 significant figure. This guy has 1, 2, 3 significant figures. Well, it doesn't matter. He's the smaller one, so we have to cut off after just 1. And we round here, and so we'd wind up getting just 2 kilograms because we only had that significant figure of 2 kilograms in the first one. Over here, we know that we are going at 6.083 meters per second, so we've got 1, 2, 3, 4. But here we've got 1, 2, so just 2 significant figures over here. So it's the smaller one, it wins out, so we have to round to here. This guy will manage to cause it to round up, and we'll wind up going to 13 meters. All right. Just a quick trig review. If you don't remember your trig, that's going to really matter at times, so brush up on that. Pythagorean theorem, a squared plus b squared, the 2 smaller sides of a right triangle, squared equals the other side, the hypotenuse squared. A squared plus b squared equals c squared. Then we've also got the trigonometric functions to relate those sides together. The sine of theta is equal to the side opposite over the hypotenuse, so this would equal b over c. Cosine of theta is equal to the side adjacent over the hypotenuse, so this would be a over c. And finally, tan theta is equal to the side opposite divided by the side adjacent, so this would be b over a. Definitely important thing to remember. All right, inverse trigonometric functions. What if we were to know what the sides of the triangle were and we wanted to find the angle? Then we use an inverse trigonometric function. The arc sine, or the sine inverse, however you want to say it, because what it's doing is it's measuring the arc of that, right? So the arc that goes along with a given ratio. So arc sine of theta equals theta. It allows us to reverse it. If we look this up, if we use a calculator, it gives us an answer. If we look it up in a big book with just a lookup table, it gives us an answer. Same basic idea. We're able to figure out all of these ratios beforehand through clever thought, and then anytime we need to figure out what the angle winds up being, we just look at the book we created, look at the table, look at the calculator. Great. So if sine of theta is equal to b over c, we could find theta with sine inverse. So theta would be the inverse, sine inverse of b over c, the arc sine of b over c. We plug in numbers and boom, we'd get what the angle is. Vectors. Vectors are a way to think about movement. In another sense, they're a way to simultaneously consider the distance and the angle, right? So v here has gone some distance and it's up some angle, right? And over here, u has managed to go some distance, and it's up some angle. But alternately, we could think of it as v went over to the right by 4, and it went up by 5. U went to the left, so it went -2, and it went up by 2. Great, so that's the idea of a vector. We can expand this. We can have vector addition. If you have two vectors, you can add them. You can put them head to tail. Numerically, you'll add their components. So if you've got v and you've got u, v plus u is just the sum of the numbers involved. So this one is 4 and -2. So 4 and -2 becomes 2. 5 plus 2 becomes 7. There we go. Simple as that. Subtraction is just adding by the negative version of a number. So if we want to know what the negative version of u was, well, negative u, we just put a negative sign in front of what it was originally, right here. We apply that in and we'll get 2, -2. So we add v to the negative version of u. So 2 plus, it was 4 before, we get 6. -2 plus it was 5 before, we get 3. Simple as that. Scalar. So vector is a distance and a direction, but a scalar is just a number. It's a way to scale a vector. It's a multiplication thing. You scale the vector, you change how much it either grows or shrinks. So you can change the length and even flip the direction of a vector by using a scalar. You just multiply each element of a vector with it. Vectors are multidimensional, scalars are just one dimension. So if s were equal to 3, then if we had v as 4, 5, what we've been using so far, then 3 would just be 1, 2, 3 out. So SV is just 3 V's stacked on top of one another. Makes sense. V plus V plus V. 3 times V. Great. If we had -2, well then we have to flip to the negative version. Here's where negative V would show up. And we stack it twice and we've got -2V. So if we want to do it numerically, we just wind up multiplying it by each component involved. 3 times 4, 5 becomes 12, 5. -2 times 4, 5 becomes -8, -10. Great. If we want to break a vector into its components, we just do it. We know what each of the components are, and so we can see how much did you move in the x, how much did you move in the y. So Vx and Vy, right? If V is equal to 4, 5, then we see that the x side must be length 4 and the y side must be length 5. Also, if we wanted to, we could say, well, V is equal to 4, 5, which is the same thing as 4, 0 plus 0, 5, which is basically what we see right here. We've added here to here, and we get to the same spot, right? If we want to find the length of a vector, we use the Pythagorean theorem. We know what those sides are because we know what the x component is, we know what the y component is. So how does the Pythagorean theorem work? Square root of the two smaller sides, 4 squared plus 5 squared, equals the other side. So we call it the absolute value, the magnitude is how we denote it. So in this case, square root of 16 plus 25, what's that going to wind up coming out to be? Doesn't come out to be a nice round number. We get the square root of 41. That's as simple as it's going to be, but that's what its length is. And if we wanted to, we could change that into a decimal using a calculator. There's a relationship between length, angle, and coordinates. So in general, if we wanted to know what it was, if we knew that our vector had a length of 5 and had an angle of 36.87 degrees above the horizontal, what would be the vector? Well, let's just make a triangle, right? Our angle here is 36.87 degrees, and this here is 5. Well, hey, this looks like a perfect time to use sine theta, right? So this side over here, let's call it y. So sine theta equals 5, not 5, but y over 5. We multiply both sides by 5. We've got 5 sine theta equals y. We plug in what that theta was, 5 sine of 36.87 degrees. Punch that into a calculator and multiply it by our 5, and we're going to wind up getting 3. So that side's equal to 3. Same basic idea over here. We'll call this side x, and anytime we're doing this, it's going to be the hypotenuse divided by the other. Cosine equals adjacent divided by hypotenuse. So anytime we want to know the adjacent side, it's just going to be hypotenuse times cosine of angle. Or if we want to know the opposite side, it's going to be hypotenuse times sine of angle. Simple as that. So x is going to be 5 times cosine 36.87 degrees. Toss that into a calculator, and we get 4. So the vector v would be its two components put together, 4, 3. And if we wanted to check that out, 4 squared plus 3 squared equals 25, which is the square of 5. So great. This checks out by the Pythagorean theorem. We've got the answer. All right, so that's basically all the math we've got to have under our belts if we want to get started in this physics course. So hope all that made sense. If it didn't make sense, go back, check some of the stuff that you don't remember from trigonometry. Just get back up to speed because we're going to wind up using a lot of this, especially when we're talking about multidimensional stuff. All right, see you at the next lesson.